lecture continuing lesson L20 on higher order linear differential equations with constant coefficients. In particular, what we're going to discuss is complex roots of the characteristic polynomial. That's where they're not purely imaginary but complex. We'll go over a few examples. So let's say we have a polynomial, say the characteristic polynomial. If a complex number a plus ib solves it, then its conjugate, replacing the second one with a minus I times b, will also solve the equation p of r is equal to 0. So last time we saw r squared plus 1 had two roots, I, and also the complex conjugate minus I. So here a was equal to 0, b was equal to 1. So 0 plus I and 0 minus I both solved. R squared plus 1 was equal to 0. They are both roots of the polynomial r squared plus 1. So let's see how this plays out when we are solving a higher order linear differential equation. So let's look at this differential equation, y double prime minus 2y prime plus 2 is 0. The characteristic polynomial is r squared minus 2r plus 2. And the characteristic equation is just setting that polynomial equal to 0. R squared minus 2r plus 2 is 0. This doesn't factor, actually. If you check this does not factor. So to solve the characteristic equation, we need to use the quadratic formula. The quadratic formula says that if ar squared plus br plus c is 0, then r is negative b plus or minus the square root of b squared minus 4ac over 2a. In this case, when we plug all those values in, we'll get plus 1 plus or minus I. These are complex conjugates, 1 plus I and 1 minus I. And they both solve the equation r squared minus 2r plus 2 is equal to 0. That is, they both solve the characteristic equation. And because they're two roots of the characteristic polynomial, we can form complex valued solutions to the differential equation. E to the I plus 1 plus I times x and e to the 1 minus I times x. So e to the x times, now if we rewrite this, e to the 1 plus I times x, that's the same as e to the x plus ix. We can factor e to the x. We're left with e to the x times parentheses cosine x plus I times sine x. Likewise, if we replace this with minus I times sine x, it just becomes minus ix becomes cosine x minus I sine x. We look at any ordering combination will also solve the equation, the differential equation. For most physical applications, we want solutions to be real valued, so we take these two solutions, 1/2 times the sum of the two, 1 over 2i times the difference of the two. We get these two solutions, e to the x cosine x and e to the x sine x. They're both real valued solutions, and it turns out they're linearly independent. So they form a two-parameter family of solutions. And that was actually promised in an earlier lecture. That was promised as for a second order linear differential equation with constant coefficients, you always get a two-parameter family of solutions. Okay. Let's look at another case. It's also possible to have some roots are just real and others are complex. Let's look at this third order differential equation, y triple prime minus 8y double prime plus 22y prime minus 20y is 0. That's just a type of thing. It's not really stable. And so this is a degree 3 equation. So there's a theorem that says it has a three-parameter family of solutions. That is, there are three linearly independent solutions, and any linear combination of those will also be a solution. So this is the characteristic polynomial r cubed minus 12r, sorry, this should have been 12r squared plus 22r minus 20. And the characteristic equation, we should have said equation, not polynomial, is r cubed minus 12r squared plus 22r minus 20 is equal to 0. You can check that r is equal to 2 solves that equation. That's just from some arithmetic. And then you can divide out r minus 2 using polynomial division to get r minus 2 times r squared minus 6r plus 10. So we know r is equal to 2 is one root. The other roots are going to be roots of this second factor, r squared minus 6r plus 10. Now, this doesn't factor. R squared minus 6r plus 10 does not factor, so we're going to use the quadratic formula. If we apply it to this, a is 1, b is minus 6, c is 10, we get r is equal to 3 plus or minus I. And what are we left with? Well, a 3-parameter family of solutions to the differential equation, because from r equal to 2, we get y is equal to e to the 2x. From the conjugate pairs of complex roots, 3 plus I, 3 minus I, we get e to the 3x times cosine x plus I sine x, and e to the 3x times cosine x minus I sine x. And we form real-valued solutions like before, e to the 3x cosine x, e to the 3x sine x. And then we form these 3-parameter family of solutions, C1, constant times the first solution, e to the 2x, constant times the second solution, e to the 3x cosine x, constant times the third solution, e to the 3x times sine x. It turns out all these functions are linearly independent. And voila, we have our general solution to the degree 3 differential equation. So here's a review of the main goal for talking about complex roots that come in conjugate pairs. If we have two complex roots that are conjugate pairs and they appear as roots of the characteristic polynomial, then the associated differential equation has the following two linearly independent solutions: e to the ax times cosine bx and e to the ax times sine bx. Okay, I will see you all on Friday.